Today I will show TurtleBot3 navigation monitoring and adaptive control project built around ROS2 and Nav2 modules. So to reproduce the work, I use the Windows 11 plus VSL terminal. So in order for you to start reproduce the same work, you need to first install the VSL, and then afterwards, I assume you follow through running the project part here, basically building and running the Docker environment for you to get started with. We open the VSL terminal. If this is your first time running the github environment, it's okay for it to take more time to launch, and you might not even see the robot spawned. So basically, after you get the window opened, you need to restart the gazebo, so you will see the robot inside the environment. So as you see, the environment has already started, and our robot is actually rotated here with its leader scans. So what we do now here, I already uploaded the map, YAML, and PGM files. So I will run, and it will start RVs for us. From here, we are able to see the scanned version of the map. So what we need to do is basically place our robot inside the map. We know our robot is around this point with this direction, and Slam will easily correct it. Here, once the robot has spawned, you're able to see the local scan, and it's highly aligned with the map. Even now, we are able to give some goals to our model, but I also want to start our navigation uh, monitoring. And how we do it is basically we come here and I run the launch file for our navigation monitoring. It basically runs the adaptive controls, navigation feedbacks, and it publishes into the topics. Once we get it, we see it started to give the metrics, and also the machine learning part, the risk navigation risk analysis takes a little bit more seconds to launch since the torch on CPU takes a bit more time to start. We also start the Flask web GUI, and this will allow us to track live changes on our metrics. Once we do this, we are able to see the web. It's already live in our local web port. So I come here and start the port, and now we are able to see our metrics. So I will show you how it changes, but before starting that, let's see if our model is actually working. So if I click here, nav the goal, and click here, you'll see that for mine, it takes a bit more time since I don't do it. Works here in this environment. So as we are seeing it, the robot is also moving in the simulated environment. I will check some cases where the robot might get stuck. I set the goal here. And actually in our codes, I implemented some adaptive controllers, which is, for instance, when it comes into narrow passages or where it comes very close to one side of the wall, it does some escape mechanisms. For instance, in places where both walls are very close to the robot, in narrow passages basically, as you see here on the narrow passage, the speed gets reduced a lot to make sure we are not hitting or doing something wrong. Or in this case, if the robot gets very close to the wall, sometimes the path planner, gives some abnormal commands to the robot. It rotates its head to the goal and it just basically gets stuck very near to the wall. So I also implemented another escape mechanism. So if the robot is very near to a wall, it basically rotates its head to the opposite side of it and goes forward for like 30 centimeters, which you can adjust in the YAML parameter, and then reinitialize its original action. Sometimes it just, for instance, I give my, let's say, goal here, and along the way, you see this red line is the path that it's following. Sometimes you just see some temporary actions for what you see. It just turn a little bit of left to make sure it's not hitting into the wall. And this is also another parameter you can adjust based on your environment. In this case, I think the 30 centimeters is quite enough for the house world, but we will check other ones, how it performs. Now our model is able to find narrow passages. I also implemented a navigation risk LSTM model, but I was only able to get data from the world, the default environment of the TurtleBot. So unless it's very near to the walls, it tends to give less risk probability. And if it has some wide areas that it can escape, it basically gives very low probability of predicted risk. But obviously it needs to see more data in the training. So a future work might be adapting it into different environments, especially in the house environment, to see how it changes. And with more data, the model might be more complex as well. But for now, I will focus on the other metrics. And we can also access the logs of how we performed during these trials, and which is saved in the logs folder after each node run, or latest log here. So it will have the timestamp, total distance, every data that our metrics collector publishes. So this one is actually used to train machine learning models. Now we also have this default world environment that TurtleBot3 package is providing us. So I also already scanned this and we are able to see the version, the localization of our robot. Now I'll check how it performs. Now we can monitor how our model performs. Now we can monitor how our nodes perform in the default world environment. Let's give one sample goal. It has started. For this one, I mean, the obstacle avoidance would be easier since it's more scattered and less dense compared to the house environment. So I assume we are not gonna hit any of the obstacles. This easily navigated its way. Let's give one another goal to very near one of the borders. Let's give here. As you see inside this environment, the robot easily navigates itself. This is also another environment I have. This replicates a simple maze that we can test our robot if it can go outside of this building, basically solving the maze. But this can also be one of the limitations of my current approach because right now I am currently working on to have more conservative path planning to turn these walls. Because now, as I will show, what happens is that it doesn't get very near to the wall, but before the wall escape mechanism is getting turned on, it basically rotates itself through the wall. So it gets stuck, it can't go near the wall, neither go back. So this is also another part that I need to investigate and solve. And let's see if it can go this part. As soon as it gets out of this small room, it has problems turning right in the next turn. You'll see around this part, it turns its head to the goal point, which makes it stuck. You see around that part, it starts to rotate itself. But since it's not very close to the wall escape mechanism is not getting turned on. You can monitor it through RQT console.